Hey everyone, welcome! Today we're diving into the world of enhancing fuzzing on embedded devices. Fuzzing is a powerful technique used to find bugs and vulnerabilities in software, and we'll explore how it can be supercharged to work wonders on these compact and specialized devices. Get ready for an exciting journey into the realm of fuzzing on embedded systems. Let's get started. Have you noticed how the number of IoT devices is exploding? They're literally everywhere, in critical infrastructure, industry, healthcare, and our smart homes. These little things are like embedded systems with custom applications, making everything so connected and convenient. But here's the catch. With all this growth, security threats are also on the rise. Those software vulnerabilities in embedded systems are becoming a real concern. We need to watch out for that. You know what the goal here is? To make IoT devices super tough and immune to those unpredictable inputs. And most of the time, these devices get their inputs from sensors. But here's the catch. Those sensor readings are wild and unpredictable, mostly floating point numbers. But don't worry, we've got a plan to make things better. We're going to do this thing called fuzz testing on... there are two key ways to boost fuzz testing and make it even more effective. First, we can work on improving instrumentations. The second way is by focusing on improving mutations. Instrumentation. These are like the eyes and ears of the fuzz tester, keeping a close watch on the code during testing. By enhancing instrumentations, we gather better insights into what's happening inside the program. This means we can detect vulnerabilities more accurately and quickly. Mutations are like the magic ingredient in fuzz testing. They're responsible for generating all those wacky and diverse inputs to push the system to its limits. By refining our mutations, we can come up with even more creative and challenging test cases. This allows us to really dig deep and uncover potential issues that might have gone unnoticed otherwise. So it's all about sharpening those instrumentations and perfecting our mutations to take fuzz testing to a whole new level. All right, so here's how this fuzzer thing works. First, the target program undergoes this thing called the instrumentation process. It's like giving the program a special upgrade, making it all instrumented and ready to roll. Now, with the instrumented program and some initial seeds in hand, we dive into the fuzzing loop. It's like this continuous cycle where we keep feeding those seeds as inputs to the target program. But wait, here's where the real fun begins. We've got this cool mutator, and it's like a seed magician. It generates new seeds, all fresh and ready to be used as inputs to fuzz the target program. And that's how the magic happens. With these new seeds, we keep fuzzing the program, exploring all sorts of possibilities and pushing it to its limits. It's like an adventure, finding vulnerabilities and making the program more robust. So, it's all about instrumenting, fuzzing, and mutating those seeds to make our fuzzer a fuzztastic success. Let's take a look at the proposed approach here. So there's this thing called a custom mutator, and it does something pretty cool. It basically takes control of the mutation process from the default mutator of the fuzzer. But here's the twist. It goes a step further and splits the floating point seeds into three parts: the sign, the exponent, and the mantissa. Once it has these segments, it goes wild and performs all sorts of mutations on each of them separately. It's like a mutation party happening segment by segment. And this clever process makes the whole mutation thing context-aware, you know what I mean? It's like the mutator is super smart and knows exactly what it's doing with each part of those floating point seeds. It's pretty awesome. Here's the deal. One custom mutator can handle all sorts of mutation techniques, but the fuzzer won't know exactly which technique is being used or which part of the floating point is getting mutated. That's a bit of a drawback, right? But wait, there's a way to fix that. We can create unique custom mutators for each technique and each segment of the floating point. By doing this, the fuzzer becomes aware of the specific technique used for mutation and which part of the floating point is being tweaked. It's like giving the fuzzer some superpowers. With this newfound awareness, the fuzzer can now create more useful inputs. It can understand the context of the floating point formats and work its magic to generate even better test cases. So, in a nutshell, creating these tailored mutators is the key to making the fuzzer super smart and effective. In this table, you can see how floating point numbers are formatted and used in programming. The table shows how floating point values are represented according to the IEEE 754 standard. According to the IEEE 754 standards, there are 5 types of exceptions that can occur in floating point operations. Overflow. This happens when the result of a calculation is too large to be represented within the given floating point format, causing an overflow of the available bits. Underflow. In contrast to overflow, underflow occurs when the result of a calculation is too close to 0 to be accurately represented in the chosen floating point format. Inexact. This exception occurs when a result is not exact and has to be rounded to fit the floating point format, introducing a slight loss of precision. Invalid. The invalid exception arises when an operation is performed on a value or combination of values that are not meaningful or defined within the floating point standard. Divide by 0. As the name suggests, this exception occurs when attempting to divide a number by 0, which is mathematically undefined and leads to an exceptional situation. So, while working with floating point numbers, it's essential to be aware of these potential exceptions and handle them appropriately to ensure accurate and reliable calculations. All right, so when it comes to floating point there are some special values we need to be aware of. Imagine all the bits in the floating point number are set to 1. In this case, we get one of these 3 special values: positive infinity, negative infinity, or NaN, which stands for not a number. Now let's talk about dBl_max and dBl_min. These are the largest and smallest finite representations of floating point numbers. It's like the upper and lower bounds for the numbers we can represent in this format. Oh, and don't forget about +0 and -0. Yep, we've got both +0 and -0 in the floating point world. It might sound a bit strange, but it's essential to keep in mind these special values to work with floating point numbers correctly. The target program was intentionally designed to have some vulnerabilities, and during the fuzzing process, these vulnerabilities were discovered. Now, to put this fuzzing to the test on a Raspberry Pi, a powerful computer was initially used as a benchmark. And you know what? The results were pretty interesting because even on the Raspberry Pi, those vulnerabilities were found. It did take a bit longer than expected, but hey, it worked. In essence, it just shows that even on a smaller and less powerful device like the Raspberry Pi, fuzzing can still be effective in uncovering vulnerabilities in a target program. Pretty cool stuff, right? Hey, let me show you the snapshots while I was fuzzing. It took quite a while, so I've included the snapshots I took at 4 minutes, 5 minutes, and 10 minutes into the process. And finally, the most exciting part, the snapshot after I found all the expected crashes. So take a look and let's see how the fuzzing journey went. Thank you. Hope you enjoyed it.